Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's lecture. In last few lectures we have been discussing the problem of harmonic oscillator and how to solve it quantum mechanically. So far we have learnt about the eigenvalues of the harmonic oscillator problem, and also we have discussed the functional form of the lowest eigenfunction of harmonic oscillator. Today we will continue our discussion from there. If you remember, we defined our phi 0, which is the lowest eigenfunction of harmonic oscillator, as we obtained the normalization constant given here, beta square, which is defined as m omega divided by h bar. This is the normalization constant, and this is the functional form of the lowest eigenfunction of harmonic oscillator. And we also discussed that this this form is known as a Gaussian function. It gives a bell shape function. If you notice one thing, the exponent of this function, the exponential function, has beta square x square. If you find out that the dimension of beta, you will find that it has the dimension of length inverse. So, if beta is length inverse, I multiply x with it, then this quantity becomes a dimensionless quantity. So, here beta square x square is actually a dimensionless quantity. We would define this dimensionless quantity beta x as rho, which is a new dimensionless coordinate. As opposed to this x, which is a coordinate with a particular dimension. And how are we going from the dimension coordinate to dimensionless coordinate? By multiplying x with this beta, which was just to remind you, beta square is m omega divided by h bar. So, by multiplying this factor with the dimension of the problem x, we get this dimensionless coordinate. We will redefine this wave function, the lowest wave function of harmonic oscillator, in the dimensionless coordinate. So, we have in the dimensionless coordinate, we have phi 0 as the normalization constant a multiplied by e to the power minus rho square by 2, where rho is defined as beta x. Now, since rho is beta x, the limit of rho is also going to be same as the limit of x, that is from minus infinite to plus infinite. And if we have to normalize this function, you would see that phi 0 star phi 0. Now, instead of normalizing it in coordinate of x, I am normalizing it I am integrating it in the coordinate of rho. This one should be 1. So, therefore, a square minus infinite to plus infinite e to the power minus rho square d rho. This is the integral that we have to evaluate, but you know that this is a Gaussian function, which is an even function. So, instead of evaluating this integral from minus infinite to plus infinite, what I am going to do is that I am going to evaluate it from 0 to plus infinite and multiply this by 2, because the integration between 0 to plus infinite is equal to integration between minus infinite to 0. So, therefore, this minus infinite to plus infinite integration gives me twice the value of the integration from 0 to infinite, e to the power minus rho square d rho, and this value I know as square root of half into square root of pi. So, this has to be 1. So, therefore, my a is going to be 1 by y to the power 1/4. So, to write down the normalized form of the eigenfunction, the lowest eigenfunction, I have in dimensionless coordinate, I have, as you would see, that this functional form is somewhat simpler than the previous one, where it depended on the dimension. Not only the simplicity of the functional form, it also provides us a bit more clarity an harmonic oscillator problem when we change from one system to another system, because now this dimension is not system dependent, because it is this rho is not system dependent because it is already dimensionless coordinate. The advantage of using this we would discuss in some detail in a future class. So, this is now the form of the wave function, the lowest eigenfunction of harmonic oscillator in dimensionless coordinate. We will continue our discussion, but before that what we will do is that we will express our step up operator, which is a plus operator. If you remember, we defined it as beta by root 2 x minus I p m omega. So, here x and p are defined in terms of the dimensioned coordinate x. Now, we would like to express this a plus, the step operator, in terms of dimensionless coordinate. So, if you remember, so we can expand this. So, this is beta x divided by root 2 minus beta divided by root 2 I divided by m omega p. So, if you see beta x, you already identified, this is rho by square root 2, because we have defined the dimensionless coordinate rho as beta into x, minus I have to do little work on the second term I by m omega, and then I define my p operator. So, this is operator p, which is minus I h bar d by dx. When you look at this term, so I have rho minus root 2. So, I see here I minus I would give me plus 1, and I am left with beta divided by root 2 h bar by m omega d by dx, but since x is rho divided by beta. So, I am writing out d rho, and then I will have to multiply this with beta. So, I am sorry, this is not, this is beta. So, d by dx becomes beta into d by d rho. So, I have beta here, beta square, and if you remember, h bar divided by m omega is 1 over beta square. So, therefore, this term becomes rather simple. All these terms they cancel out, they become 1, and then I am left with this simple form. So, I can further simplify it by, so in dimensionless coordinate my step up operator also becomes somewhat simple. I can similarly show step down operator as this is the step down operator and this is the step up operator in dimensionless coordinate. We would now continue our discussion as to the point that so far what we have done is that we have obtained the functional form of the lowest eigenfunction, that is phi 0, but we do not know what are the functional forms of other eigenfunctions of the harmonic oscillator problem, and that is what we are going to discuss next. So, we have phi 0 as a normalization constant multiplied by the Gaussian function e to the power minus rho square by 2. This is in dimensionless coordinate. We know that but we still do not know what is phi 1. To obtain phi 1, what we will do is that we will apply this step up operator a plus on phi 0, and this we know is proportional to phi 1. When a plus, the step up operator, acts on phi 0 function, it gives me phi 1. So, I know what is the functional form of a plus operator. So, let us do this. So, I am continuing this discussion. So, this is proportional to 1 over root 2 rho minus d by d rho. This is a plus operator in dimensionless coordinate. Phi 0, instead of writing phi 0, I will use the functional form. So, I have a which is a normalization constant. I am keeping that constant here and writing down e to the power minus rho square by 2. The reason why I am bringing this to the left side, you see that it is important for you to realize that this is an operator which is a rho, whose action is simply multiplication, but this is a differential operator. So, I have to differentiate this function with respect to rho, the function that comes after this operator. So, now what you see is that I have some normalization constant, I again have to renormalize this new function. So, therefore, in other words, I can write down this, instead of using this proportionality, I am writing down this normalization constant and I am putting all these constants into a new constant, I am calling it A1, and simply I have the form So, this to get phi 1, what would I have to do is that I have to make calculate what is the action of this operator, a plus operator, the step up operator on this function. Fine. Now, to get phi 2, what would I do? Phi 2 I know is I can obtain phi 2 when I apply step up operator on phi 1. So, this is a phi 2 is proportional to a plus operator on phi 1. I know this is phi 1. What is phi 1? Phi 1 is action of a plus into phi 0. So, therefore, this is equivalent to a plus phi 0, because phi 1 is proportional to a plus phi 0. So, therefore, to obtain phi 2, I have to apply this a plus operator twice. What can I write? I can write this phi 2 as some normalization constant a 2. I have to individually normalize this eigenfunction phi, this a 2 multiplied by 2 times this operator, a plus operator, rho minus d by d rho. And this operator is going to act on this function, this Gaussian function, e to the power minus rho square by 2. Similarly, if I have to get phi 3, I will have a normalization constant a 3 multiplied by the action of this step up operator thrice on this function phi 0. So, this is my phi 0, the lowest eigenfunction whose form I derived. Now, phi 1, the second eigenfunction of the harmonic oscillator problem, I will obtain by applying this operator on the lowest eigenfunction e to the power minus rho square by 2. The second eigenfunction I would get by applying this operator twice, rho minus d by d rho, and one more time the same operator, and I will have to apply this operator twice on this function e to the power minus rho square by 2, which is the lowest eigenfunction. So, if I know the lowest eigenfunction phi 0, I can simply keep on applying the step up operator as many times to get my higher eigenfunctions. So, this is phi 2. So, to get phi n, I will have to apply this operator n number of times. You might wonder that this calculation would become very complex to do when n is anything greater than 1 or 2, or when it becomes 3, you can try it out for yourself. When n is equals to 3, then this action, this one action of this operator on this becomes very difficult, although it is possible to do, but it is difficult. You may wonder as to why then we are expressing our eigenfunction in this form. The reason is simple, because we know something important about this function. The application of this operator on this function actually gives us a well known polynomial, which is what we are going to discuss next, is known as the Hermite polynomial. So, the general form of this, the eigenfunctions of harmonic oscillator is given here, which is phi n. It has got a normalization constant a n multiplied by this h n, which is Hermitian operator. This H n Hermitian operator is H n in this Hermitian operator, excuse me, this n, this is called Hermite polynomial. So, in this case n is the nth order Hermite polynomial in the coordinate of rho. This H n is coming when you are applying this step up operator n times, rho minus d by d rho to the power n. When you apply that function on e to the power minus rho square by 2, you would actually get Hermite polynomials. The Hermite polynomials of first few lowest orders are shown here. When the 0th order Hermite polynomial is very simple, this is simply 1. The first order Hermite polynomial is simply 2 rho, second order is 4 rho square minus 2, and so on and so forth. These Hermite polynomials are often found tabulated in many textbooks. So, what happens, the advantage of writing down the harmonic oscillator eigenfunction in this format is that it is very easy to write down any order eigenfunction of the harmonic oscillator corresponding to any value of n. We simply need the corresponding Hermite polynomial. We will do that. We will write down now the first few, the lowest few eigenfunctions of harmonic oscillator. Let us see what is phi 0. We have already derived it accurately, but then we would use this functional form to write down this expression. So, when n is 0, so I have a 0 which is the normalization constant, and the fourth 0th order Hermite polynomial is simply 1 e to the power minus rho square by 2. So, you can see this is simply a 0 e to the power minus rho square by 2. This is the form we have already seen. So, this is phi 0. Now, when I want to write down phi 1, that means the second eigenfunction of harmonic oscillator, I will take in this equation n equals 1. So, when I do that, I have a 1 which is the normalization constant. Now, the Hermite polynomial of first order which is 2 rho, and then e to the power minus rho square by 2. So, you see that I still have to get this the normalization constant a 1. In fact, by using the properties of Hermite polynomials, that there exists a general form of this normalization constant a n, which is given here. You can use the different values of n to obtain the normalization constant, but then you should also be able to normalize any other function. For example, take this rho e to the power minus rho square by 2, which is phi 1, and try to normalize it independently, and you see whether you are obtaining this expression or not. So, a 1 2 rho is e to the power. So, this is phi 1, this is phi 0, and similarly when I try to write down the eigenfunction of corresponding to n equals 2, when n is 2, we can write down the eigenfunction phi 2 as a 2 multiplied by the Hermite polynomial 4 rho square minus 2 multiplied by e to the power minus rho square by 2. And similarly, this is my phi 2, the phi 3 would be a 3, the third order polynomial Hermite polynomial 8 rho cube minus 12 rho into e to the power minus rho square by 2. So, as you can see, it becomes very easy to write down the eigenfunctions of harmonic oscillator in this manner. So, to remind you, the eigenfunction of harmonic oscillator has 3 important components: one, the normalization component a n, the Hermite polynomial, and the Gaussian function e to the power minus rho square by 2. So, remembering these facts, you can actually write down the any eigenfunction of harmonic oscillator very easily. One more thing you should you can see here is that the lowest eigenfunction of harmonic oscillator has only the Gaussian function, which we already have discussed is an even function. When you look at the second eigenfunction phi 1, you see that this has e to the power minus rho square by 2, the Gaussian function, which is an even function, but it is multiplied by rho, which is an odd function. When you multiply an odd function and even function, you actually get an odd function. So, therefore, phi 0 is an even function, phi 1 is an odd function. You would see that phi 2 has 4 rho square minus 2, and this 4 rho square, the polynomial 4 rho square minus 2 is even. So, therefore, phi 2 is an even function, and phi 3 you can see for yourself is again an odd function. So, the eigenfunctions of harmonic oscillators have opposite parity. The consecutive eigenfunctions have opposite parity. If phi 0 is even, phi 1 is odd, phi 2 is even, phi 3 is odd, and so on and so forth. The other thing that you would like to notice here is that when I have this functional form of rho into e to the power rho square by 2, you would see that I am multiplying two functions, one rho, another this bell shaped Gaussian function. The bell shaped Gaussian function we have already seen this. So, the functional form would be this would be a Gaussian function e to the power minus rho square by 2, which is symmetric around x equals 0, and when I multiply this with a rho to get this function. So, this is my 0. So, I have other function is, so when this is my rho axis, rho is 0, rho is plus infinite, rho is minus infinite. The e to the power minus rho square by 2 term is the Gaussian bell shape form, rho is simply the straight line here. So, when I multiply these two functions, you would see that at rho equals 0, the wave function will become 0. Why? Because this function will develop a node, that means where the wave function will vanish when rho is equal to 0. Come here, look at this value, look at this phi 2 form, e to the power minus rho square by 2, this is a Gaussian function. Now, I have to multiply this with a polynomial which is 4 rho square minus 2. I can see where this 4 rho square minus 2 becomes 0. So, if I find out the values of rho where this function will become 0, then I would know at what values of rho I will have the nodes in these wave functions. Similarly, in this expression also you can find out what are the values of node or what are the values of rho where the wave this polynomial will become 0, and when this polynomial becomes 0, the entire wave function becomes 0, and the wave function will develop a node at that point. So, the nodal structure of the harmonic oscillator eigenfunctions are derived from this Hermite polynomials. You can see that the zeroth order Hermite polynomial has no rho dependence. So, therefore, the phi 0, the lowest eigenfunction of harmonic oscillator, has no node. On the other hand, the second eigenfunction of harmonic oscillator, which has a Hermite polynomial of rho, and there exists only one value of rho where this form becomes 0, and that is rho equals 0. So, therefore, the second eigenfunction of harmonic oscillator has one node. The third eigenfunction of harmonic oscillator can have two nodes, because I have got a second order polynomial here. So, therefore, at two different values of rho, the Hermite polynomial will become 0, and therefore, the wave function will become 0, and I will get two nodes in this third eigenfunction. And similarly, and for phi 3, I will get 3 nodes, or at 3 different values of rho, the wave function will become 0. So, next what we will do is that we will discuss how these wave functions appear . So, this is the harmonic oscillator potential. If you see if you remember the energy eigenvalues that we discussed when n equals 0, 1, 2, 3, the energy values are all equispaced. So, just to remind you, the energy here is h bar by omega, this is 3 by 2 h bar omega, this is 5 by 2 h bar omega, and so on and so forth. And this is the lowest eigenvalue or the lowest state of harmonic oscillator, and the energy that it has is called the zero point energy. Now, what we see here are the eigenfunctions of the harmonic oscillator, their functional form. You see the rho for n equals 0. So, this is for n equals 0, this is a bell shaped Gaussian function. When I multiply the for n equals 1, I have 2 rho into e to the power minus rho square by 2, that is the functional form. So, therefore, you see at rho equals 0. So, this in the x axis I am plotting rho, y axis I am plotting phi. So, you can see at rho equals 0 I am developing a node, and I have got only one node, and in case of phi 2. So, this is phi 2, this is phi 3, this is phi 1, and this is phi 0. In case of phi 2 I have got two different nodes. Please remember these values are actually not nodes, actually they asymptotically approach 0. So, at long distance they would actually become 0, but they do not have a nodal structures there. So, these are the two nodal points here, and in this case phi 3, these are the three nodal points that I see. When these are the wave functions, I can show you now the phi n square. So, this is phi 0 square, phi 1 square, phi 2 square, and so on and so forth. One thing that you notice is that again the nodal structures can be found. So, this is the probability density at this point becomes 0. So, these are the points where you have node, because that is where the probability density vanishes, and these are the probability density of the corresponding to the wave functions of the harmonic oscillator. So, in today's lecture we discussed the functional form of harmonic oscillators. We started from the lowest eigenfunction of the harmonic oscillator, and then we applied the step up operator repeatedly, and thereby we generated higher eigenfunctions. That is why we also call this step up operator as creation operator, because by acting this step up operator on the lowest eigenfunctions, we simply create higher and higher states. Then we also came across that there exists a general definition of these eigenfunctions of harmonic oscillator, which has a normalization constant, a Hermite polynomial, and a Gaussian function e to the power minus rho square by 2. We also discussed that the eigenfunctions of harmonic oscillator have definite variety. Some of them are even, some of them are odd. The odd and even functions appear consecutively, and we also discussed what are the shapes of these wave functions and what are the shapes of the probability distribution for corresponding to these wave functions. We will continue our discussion on harmonic oscillator in the next class. Thank you for your attention.